Humans are like sailors on a ship called time. For us, measuring time is more than simply counting numbers. It's like checking a compass to see where we are and where we are going in this vast universe. Today, this compass is synchronized across the entire world using a single standard called Coordinated Universal Time, UTC. You can even check this precise time on your smartphone. But have you ever wondered how this standard time, the time we access so easily every day, is actually determined? Behind this precise time that we take for granted lies one of the greatest achievements of human engineering, the atomic clock. This device defines 1 second by capturing the oscillation of cesium atoms, and it is so precise that it loses only about 1 second every 100 million years. But recently, the scientific community has begun a new challenge that could surpass even this astonishing record, a device known as the nuclear clock. Instead of the atom's outer shell, this technology looks deep into its heart, the nucleus. What exactly is a nuclear clock, and why do we pursue such extreme accuracy? In today's video, we will explore the nuclear clock, a technology that could change the future paradigm of time measurement. Before we dive in, make sure to hit that subscribe button down in the corner. Now, with that out of the way, let's jump right into it. In the past, it was enough for a day to be roughly measured. Even timekeeping tools with significant errors like sundials or water clocks were more than sufficient for everyday life. But in modern society, time has become an absolute reference. It dictates the order of countless events. Take aviation, for example. When hundreds of aircraft share the same airspace, their positions and flight paths are coordinated through precisely synchronized timing. If the reference time used in air traffic control drifts even slightly, an aircraft's position and trajectory could be misinterpreted, leading to direct and severe safety risks. In modern aviation, GPS-based positioning is central. GPS calculates location by measuring the travel time of satellite signals. A timing error of just 1 nanosecond results in a position error of about 30 centimeters. For aircraft moving at high speeds, even tiny timing errors can quickly translate into significant position errors. This is why the aviation industry demands an extremely precise time standard to maintain accurate positioning. The same is true for high-speed communication networks and financial trading systems. In these environments, determining who acted first is critical. Even a microsecond of error, let alone a millisecond, can flip real-world outcomes. This is why modern technology demands timekeeping at an extreme level of precision. The revolution in modern timekeeping began in the 1950s with the introduction of atomic clocks. Researchers began asking a fundamental question: how can we measure time with zero error and maintain that precision indefinitely? To do that, the basic unit of time, the second, had to be defined in a way that anyone could reproduce in exactly the same way. This led scientists to focus on a particular atom, cesium. The electrons inside a cesium atom do not remain in a fixed state. Because of the influence of the nucleus, they move back and forth between two energy states, and when this change of state occurs, the cesium atom produces a very stable electromagnetic wave that oscillates exactly 9,192,631,770 times per second. In other words, by simply counting these oscillations, we can measure time with remarkable accuracy. A device that tracks time using these electron state changes is what we call an atomic clock. Interestingly, strictly speaking, an atomic clock is really a clock that relies on the electrons inside an atom. The accuracy of these atomic clocks is astonishing, with an error of only about 1 second over roughly 100 million years. Beyond cesium, rubidium-based atomic clocks are also in operation. These atomic clocks are actually installed on GPS satellites, providing an accurate time standard for the entire world. Given their incredible stability, it might seem that atomic clocks could serve as an absolute standard indefinitely. However, even atomic clocks have their limitations. The limitation comes from the electrons themselves. Electrons are strongly influenced by their external environment. In particular, they are sensitive to magnetic fields, electric fields, and changes in temperature. As a result, operating an atomic clock requires highly specialized equipment to minimize external influences on the electrons. In practice, reaching the highest level of performance still requires a highly controlled and sophisticated environment. To overcome the limitations of atomic clocks, a new concept was proposed: the nuclear clock. First, let's take a quick look at how it works. When people hear the word nuclear, they often think of things like nuclear bombs. However, nuclear clocks have nothing to do with explosive energy. More precisely, they are timekeeping devices that use the energy levels of the atomic nucleus. Let me explain this with a simple analogy. What happens when you're in a really good mood? You feel full of energy, like you could take on the world, but that high doesn't last forever, does it? After a while, that burst of energy fades and you settle back into your normal, calm state. Interestingly, the atomic nucleus behaves in much the same way. Usually it stays in a stable state, but under certain conditions it can be pushed into a higher energy state called an excited state. And just like our mood, that state doesn't last forever. After some time, the nucleus eventually returns to its peaceful state. And this is where something very important happens. As the nucleus falls from the excited state back to its stable state, the energy difference between the two states is released as light called gamma radiation. And this light is the key that transforms the nucleus into an incredibly accurate clock. But this raises an interesting question. How can light possibly be turned into a unit of time? In fact, this principle is almost the same as the atomic clock we briefly discussed earlier. The light emitted by the atomic nucleus has a characteristic frequency. In other words, this light oscillates a precisely defined number of times every second. For example, imagine a light oscillates exactly 5 times per second. In that case, just as one tick of a clock's second hand marks 1 second, the moment this light oscillates 5 times becomes 1 second. In the end, by counting how many times a repeating oscillation occurs within a fixed period of time, we can define time with very high precision. This is exactly the fundamental principle behind the nuclear clock. Interestingly, the concept of a nuclear clock was actually proposed around the same time as the first atomic clocks, but realizing it in practice proved to be an immense challenge. The key to a nuclear clock is exciting the atomic nucleus into a higher energy state, and the principle used to do this is called resonance. You've likely seen a famous example of resonance in a video of the Tacoma Narrows Bridge. In that video, the bridge sways violently, almost as if it were dancing before it finally tearing itself apart. Every object has its own natural frequency. When an external force repeatedly pushes at that same frequency, the motion grows larger and larger, much like pushing a swing at just the right moment to make it go higher. The atomic nucleus behaves in much the same way. To excite a nucleus, you must shine light whose frequency exactly matches the natural frequency of the nucleus. However, triggering resonance in a nucleus requires an extremely high frequency, which translates into an enormous amount of energy. This means we need a light source that's not only extremely high in energy but also precisely controlled. One such tool is the laser, because lasers can produce light with a very precise and well-defined frequency. However, there was a major obstacle here as well. To excite most atomic nuclei, you need light with extremely high energy. The problem was that building a laser that could reach such high energy while still allowing its frequency to be controlled with extreme precision was incredibly difficult in practice. Because of this, scientists needed a special element whose nucleus could be excited even with relatively lower energy. For a long time, this challenge kept the idea of a nuclear clock hidden behind a huge technical barrier. But things began to change in the early 2000s when researchers started paying close attention to an element called thorium. Thorium turned out to be special. Its nucleus can be excited with light in the ultraviolet range, with energy only slightly higher than visible light. Furthermore, the light emitted by the thorium nucleus oscillates about 2 quadrillion times every second. This incredibly high frequency allows us to divide time into exceptionally fine intervals, far beyond what current atomic clocks can achieve. For this reason, thorium quickly emerged as the most promising candidate for building a nuclear clock. Then, in 2024, a major breakthrough finally arrived. A research team at the University of Colorado Boulder succeeded in precisely measuring the frequency of the light emitted by the thorium nucleus. An idea first proposed in the mid-20th century had, after nearly 50 years, finally begun to turn into a realistic technology. Reflecting the significance of this achievement, the journal Nature, one of the world's most prestigious scientific journals, selected nuclear clocks as one of the 10 scientific breakthroughs to watch in 2024. This suggests that nuclear clocks are no longer just a theoretical concept, but a technology that's steadily moving closer to reality. There are 2 main reasons why the scientific community is paying close attention to nuclear clocks as the next frontier in timekeeping. As we've seen, atomic clocks rely on electron oscillations. However, electrons sit in the outer region of the atom, which makes them highly sensitive to their surrounding environment. As a result, atomic clocks require sophisticated shielding and control systems, inevitably making them larger and heavier. Atomic nuclei, on the other hand, are shielded deep within the atom's core. Because of this, they are far less affected by external environmental factors than electrons. This inherent stability allows them to operate reliably without the need for massive support systems, paving the way for clocks that are significantly smaller and lighter. This kind of miniaturization is especially important for weight-sensitive systems like satellites. Making the clock smaller and lighter could reduce launch costs and free up valuable space for additional scientific instruments. But even more striking is the improvement in accuracy. While current atomic clocks lose about 1 second every 100 million years, a nuclear clock is theoretically expected to drift by only about 1 second over 3 billion years. With this remarkable level of precision, nuclear clocks could become a new standard for measuring time. However, the reason nuclear clocks are attracting so much attention goes beyond simply building a more accurate clock. They may also open the door to entirely new areas of science, reaching far beyond the role of measuring time. One compelling example lies in the study of gravitational waves. These are ripples in the fabric of space-time created when massive objects such as black holes or neutron stars move or collide. When this happens, not only space but time itself changes ever so slightly. With an instrument as precise as a nuclear clock, scientists may finally be able to detect these tiny variations in time. That could give us new clues about how black holes and neutron stars collide, merge, and evolve. Another fascinating possibility is the hunt for dark matter. Dark matter is believed to make up about 85% of the matter in the universe, yet its true nature remains unknown. Some theories suggest that dark matter could cause extremely subtle shifts in the energy states of atoms or atomic nuclei. With the extraordinary precision of nuclear clocks, scientists may be able to detect these tiny changes, opening a completely new way to search for dark matter. Today, we've explored the evolution of the clocks humanity has built to measure time, and the next step in that journey, the nuclear clock. A nuclear clock is not simply about building a more accurate timepiece. It could become an entirely new scientific instrument, one that allows us to explore some of the deepest mysteries of the universe, including gravitational waves and dark matter. Whether it is detecting gravitational waves or searching for elusive dark matter, the nuclear clock may offer a new lens through which we can study the universe. It's fascinating to imagine how this next leap in precision might change the way we measure time, and perhaps even reshape how we understand the universe itself. Alright, that wraps up today's video. Thanks for watching, and I'll see you next time with another interesting story. This is Dr. Saivera Studio.